Our next speaker, he's a spaceship enthusiast who spends his time making fancy websites and building creative projects. His favorite is Thorium, an open source starship bridge simulator. When he's not coding, he enjoys rock climbing, baking, and experimenting with CSS. So today, he'll be sharing what the web can learn from video game networking. So please welcome Alex.
Hello, everyone. Oh, I can do it myself? Yes. Incredible. Except, oh no. There we go. Hi, everyone. I'm Alex. I make fancy websites for an agency called EchoBind. If you need help making fancy websites, you should hire us. That's echobind.com. And if you want to go to one of the other talks, this is the problem with 3-track conferences, is you have to choose. So if you really wanted to go to a different one, I'll give you the TLDR. We're going to talk about latency and bandwidth today. So to improve latency, you can speed up your server's response time, use a server-side cache like Redis, move your origin server as close as possible to the user, and use a CDN for static assets and caching if you can. Finally, route your internal traffic through the same data center or cloud, including putting your database as close to your origin server as possible. This helps avoid unnecessary internet router jumps. This is all stuff that I hope you've heard before, but if you haven't, hey, now you know. And then to improve bandwidth, send less stuff. So compress your images, ship less JavaScript, do lazy loading, code splitting, tree shaking, all of that stuff. Use server-side compression. Broadly, for regular assets, you can use something called message pack to compress your JSON data into a binary string. And if your data is a well-known structure, you can compress it even further using binary serialization, which Tyler Benfield actually talked about earlier today, which is really cool. And that can give you even smaller packet sizes. And finally, if you can, see if you can send patches of data instead of the whole packet of data when you're sending updates. OK. If you want to go, you can go. The rest of us, let's chat, which is what we love to do, right? Humans love to communicate about all kinds of things, and that is why we're here today. Fun fact, human speech, regardless of language, has a bandwidth of about 39 bits per second. And since the speed of sound is about 343 meters per second, those of you in the back, I am communicating with you with a latency of about 60 milliseconds. Hello. Yeah, there, and that right there, that was like a UDP connection. So to make sure we're all talking about the same thing, when I talk about bandwidth, I'm meaning bits per second, the maximum amount of data that can be sent over some medium in ideal conditions over a given period of time, measured in bits per second. So if the signal is poor or noisy, or if you need to repeat a message, the effective bandwidth will be lower. And then latency, we just measure in time, how long it takes for a message to be received after it is sent. Usually it's helpful to talk about round trip time, but today, when I say latency, I'm talking one way. So, fun fact, the latency of the universe is the speed of light divided by distance, since nothing can go faster than the speed of light yet. Which means the best case scenario for sending a message to your antipode, that is the point on the opposite side of the globe, is 21.25 milliseconds. I can't remember if that is just there. I know I said it's just not the round trip time, it's just there. I think this is just how long it takes to get to the other side of the world if you go all the way around. So in ideal conditions, that is your fastest latency if you are sending messages to the middle of the Indian Ocean. And distance plays a big role in both bandwidth and latency. Humans realized pretty early that being able to send messages quickly over a long distance was pretty handy. But mechanical methods, like these, are highly limited and require relays to send over very long distances. Fortunately, we were able to, add physics to the equation, harness the power of physics, and send more signals further and faster. And it still just blows my mind that TV signals are in the megabit range, which is crazy. That is a lot of data very fast. And then digital communication has made it so that we can send unfathomable amounts of information across the world, literally at the speed of light. It is now possible for us to send and receive video and audio from anywhere in the world almost in real time. And it is kind of magical, and it's taken a lot to get to this point. Another fun fact, you know, Alexander Graham Bell invented the telephone, which is great, but he also invented the photophone, which uses light to transmit audio. So fiber optics way back in whenever Alexander Graham Bell invented the photophone. One of these things, all communication methods have in common is protocols. Sending signals is one thing, but knowing what that signal means is something entirely different. Telegraphs use Morse code, modems scream at each other to initiate a connection. In fact, we're going to listen to it now, just for old time's sake. And if you know this one, feel free to sing along. Classic. The world was better when our thinking boxes of silicon just screamed at each other. So you might have seen this diagram before. This is the hierarchy of protocols we use over the internet. It is called the OSI model. It is holy and revered. And each layer of abstraction hides the lower layers so you don't have to think about them. And everyone has opinions about where each layer goes and what it does. Don't yell at me if this doesn't exactly match your expectation, okay? It's complicated. For practical reasons, it's harder to reinvent the lower layers. So due to protocol ossification, which literally means turn into bone, the lower 4 layers have pretty much stabilized. We're going to use fiber optics and twisted pairs for the physical layer, Ethernet for the data link layer, the internet protocol for the network layer, and TCP and UDP for the transport layer. Us web developers, we hardly have to think about those things. We just live up in that big orange box up there, and we squish those 3 together. Is anyone not familiar with TCP and UDP? Raise your hand high in the air like this. Oh, good. Then you're going to get my jokes. Are you ready for the TCP joke? Okay, I'm going to send the TCP joke. Here's the TCP joke. Did you get the TCP joke? I'm sorry, there's a connection error. Let me send it again. I'm kidding. And I can try telling the UDP joke, but you might not get it. Thank you, thank you, thank you. I am a dad, yes. And that brings us to the elephant in the room for us web developers. Browsers don't support UDP. I mean, technically, you can use WebRTC, which is a peer-to-peer UDP protocol, even between a client and a server, but setting it up is a pain. I mean, STUN, ICE, MCU, SFU, what a mess of alphabet soup. No thank you. Native game developers, on the other hand, can take advantage of UDP to reduce the overhead of the TCP handshake, which is a lot. And when you're trying to do real-time simulation, animation, whatever, over the network, those little delays add up. But since browsers can't use UDP because of security, I mean, why don't we just give everyone a DDoS box in their web browser? Sounds fine to me. We have to accept the limitations of TCP, which means you can't build your own protocol on top of UDP. You have to send triple the packets for one message, and you have to wait for every packet to be acknowledged before the next one is even sent. In my experience, though, and for anyone who's ever played a networked real-time video game in a browser, it hasn't mattered too much. You can engineer things around it. For example, there are some tricks to speed up TCP for websites. This website here is a blog that talks about why your website should be under 14 kilobytes in size. That is a cool URL. To determine bandwidth, web servers usually send 10 TCP packets at first, which ends up being about 14 kilobytes, given that every Ethernet packet is 1,500 bytes, but we have to have a little bit for all of the other protocol headers before we get to the actual HTTP message. So that includes HTTP headers, HTML, CSS, JavaScript, and images. So if you can get your entire website down to less than 14 kilobytes, in high latency situations, it is going to make a big difference. So to demonstrate this, I have a demo. That's why it's called a demo, I guess. So you can scan this QR code, and you can play this game in real time with everyone else at the same time. We're going to play this networked video game, It is this kind of skill game with paddles and balls, and we're going to call it ping. And yes, the paddles are very small to make sure that we can fit everybody on there, okay? So take a look there at that bandwidth number. My goodness. We're going to talk about requirements for a second. This should feel the same as playing the game locally. We want it to feel fast on everybody's devices. And the ball should be in the same place at the same time for every player. So the trick is synchronizing each player while accounting for bandwidth and latency, okay? So we're going to start with bandwidth. The real-time data, the data sent frequently between clients to keep the game in sync, depends on how precise your rendering is. We could just use JSON, which is what I'm using now, which requires more than 3,000 bits per second for 2 players, and for how many players? I should have put the number of players on there. Sorry, guys. But the bandwidth is getting into the 37,000 bits per second area, so that's cool. If you want a smaller serialization format than JSON, a quick and easy solution is a package called MessagePack, which serializes JSON on one side into a much smaller binary format on the other side, which you can then deserialize back into JSON. So let's do that right now. I'm going to come over here, find my mouse, and click on MessagePack. And it's going to freeze until I do this. And then it's going to work again. Did it work? No? Oh my goodness, we might have. Good job, everybody. Nice. Yeah. Goodness. Is my internet connection broken? Okay, then. Give me half a second to try in a new tab. Oh, I know what the problem is. There we go. Okay. Let me just make sure we're synchronized properly. Okay. And are we on the right? I guess it's there, but the game isn't playing. Huh, that's a shame. Sorry, everyone. I wish that my demo was working, but apparently it's not. So just for our purposes today, we are going to just run it locally. You won't be able to play around with it yourself. I'm sorry, guys. That's the curse of demos. So I'm just going to open this up. And hopefully it pulls up. There we go. Oh, and I need to do one more thing, and then I'll put it on the slides. I promise, I'm doing something. Nope. That is not what we want. Okay. Oh. There we go. Okay, here's the demo. We just have 2 players right now, and you can see that it is going a little bit jumpy, and you can see the bandwidth over there. Let me try turning on MessagePack again. And then just, oh, did that work? Yeah, you can see that it's a little bit lower, maybe? Yeah, it decreased. Okay, great. So it gives us a little bit of benefit. Just remember that anytime you're doing any kind of serializing or deserializing, there is going to be some CPU overhead the more complicated it is. I actually haven't done any benchmarks on serializing or deserializing. So can we make it even smaller, though? If you went to Tyler Benfield's talk earlier today, you know the answer is yes. We know the exact format of this data. We're looking probably at around 10 bits per dimension. So we have a Y dimension for each paddle. So that's 10 bits each. And then another 10 bits for the X and Y position of the ball, which has frozen. That's inconvenient. So for 2 players, that means 40 bits. If we're sending 30 frames a second, we're looking at 1,200 bits per second, which is well within the range of dial-up modems. That's a pretty good serialization format, albeit a little manual. And then there's even more that we can do. At the HTTP server level, we can further compress everything. We serve by reading the accept encoding header, which comes from the browser. That way, the browser can tell the server what it knows how to decompress. So the server knows which compression algorithm to use, like Brotli or gzip, to compress assets before sending it to the client. Most HTTP servers do this automatically, but you should double check just in your browser network tools. You can see the headers and see what compression is coming through. And then we'll do everything we can to keep all of the other assets small. Compress images, use efficient formats like SVG instead of PNGs, and OGG instead of WAV for audio. Those are much smaller, much more compressed. You can minify your JavaScript. You can use bundler tricks like code splitting and lazy loading, all of that stuff. We're going to come back here to the slides because this is a pretty interesting article that I read, which says minification doesn't matter much. The idea is that minification automatically compresses things by removing stuff that isn't necessary and getting rid of white space and all of that stuff, renaming your variables. The thing is, compression algorithms are really good, and they're able to take that unminified JavaScript and give it about the same amount of compression as you would just minifying, without obfuscating your front-end code in production. So your mileage may vary. Be sure to test it with your own benchmarks and make sure you're using server-side compression. Now let's talk about latency, and we're going to come back here for this one. Let me see if I do this. There it goes. It's moving again. And you can see how much smaller it is when I use my byte serialization. OK. So Pong isn't an especially twitchy game. It's not like a fighting game, but you don't want to be several frames behind when you're trying to block the ball. If we're going peer-to-peer, from here in Utah to players all over the world, we can expect latency anywhere from 30 milliseconds to 300 milliseconds. That is not good if we're animating every frame sent over the wire. So how do we fix this? For starters, we might not be able to put our players physically close to each other, but we can shorten their internet distance by putting the server closer to all of the players. So that's why when you play video games online, you'll have regions. Here's a few examples of some routes that packets might take depending on where you're sending them from Utah. So this right here is Cloudflare's network going to their DNS service, 1.1.1.1. And it goes down from Salt Lake to Provo and then over to Toronto, and that's where it resolves. I use the traceroute command in order to find out all of these. You can do this yourself. You don't have to be like a crazy hacker. Or you can be a crazy hacker. No judgment. I'm not going to stop you. This right here is Google. Google's 8.8.8.8 DNS service. It goes down to Provo, then over to California, and then over to Atlanta, Georgia. And that jump is also going to add some latency that can't be resolved. There's nothing you can do to stop that latency other than change the route. Here's Amazon going down and then over to Colorado and then up to Washington. And just for fun, my spaceship game, Thorium, it's hosted on a hosting company called Railway. And this is how you get to that server. It goes over to Colorado again and then over to San Francisco area. Just for fun, let's trace our route through the open internet to Africa. And we see here there are several transatlantic jumps back and forth before eventually we end up in Egypt, and then we get down to South Africa after 19 total jumps, which does seem like kind of a lot. And this was to a South African government website. I don't know what they probably aren't expecting to get a whole lot of traffic from Salt Lake City, Utah, but the back and forth was a little bit surprising. So if you are able to move your traffic through a single cloud, it can really help with latency by decreasing the number of hops, because a cloud probably knows what data centers to route you through in order to get you to your destination faster. So you keep it all in a single network. That network knows how to get things where they need to go. And it's the same reason why you should put your database in the same data center if possible, if not in the same cloud, so that when your origin server is making requests to the database, it doesn't have to make a whole bunch of hops. It can just go straight to the database. Or just use SQLite, and then you don't even have to make a network hop. It's just a file system call. Come on, guys. It's 2025. So if you're going to access an AWS database from a GCP server, you are just asking for trouble. And this is especially relevant if you use a third-party service alongside your main cloud, like Neon, the database, or Firebase, the database, or PlanetScale, the database, or Upstash, the Redis. Speaking of Redis, if you've got more than one server across multiple regions and data centers, And you can't just put your origin server next to all of them because of the CAP theorem, which I'm talking about the CAP theorem in a talk again. I'm sorry, everyone. If you haven't ever looked up the CAP theorem, go look it up and then cry, because it's sad that we can't have our cake and eat it too. So instead, you need to use a cache, something where after you've gotten the data from your origin database, you bring it back to your region server, cache it, and then the next time you need that data, it's right next to you. You don't have to make that big, long jump again. Networked video games try to do this by keeping all of its data in memory if possible, so that all of the simulation and animation is just happening on the same device as quickly as possible. Web apps, we can get away with a memory cache running next to our server instead of in the memory of the server itself. But if you want to do that, I'm not going to stop you. Like, you can go ahead and get a massive box. Be my guest. So if you want to decrease latency in a normal web app, put the cache next to the server so it doesn't have to make those requests to the database over a long distance. And then front your server with a CDN that uses anycast routing, like Cloudflare as an example. There are other CDNs that do this. This takes advantage of a quirk of IP, remember that protocol from back then, by letting multiple servers across the world have the same IP address. So when you make a request for that IP address, you are going to get routed to the closest by time server, and then at that point, you can go through your CDN's network, your CDN's optimized network backbone to get to your destination and back as fast as possible. Plus, you can use that CDN to distribute assets, so the latency for fetching those assets is always as low as possible because they're really close to your consumers. They can get them from the closest CDN node. Okay. No, they are visible. There's just nothing on them because I was expecting there to be a Pong game going. Thank you. Very helpful. So we've done everything we can to decrease latency. What can we do at this point? Distant users or users with a spotty connection might still have a bad time, but that doesn't mean that they're disqualified from playing. So let me come over here and pull up our Pong game again, my local Pong game. And just for fun, I'm going to click this interpolate button. Whoa. It's smooth, incredible. Wow, how did that happen? What I'm doing is I'm sending information about the packets ahead of time to each of the clients. So the simulation that's running on my computer is just a couple of frames behind, but by doing that, I'm able to interpolate the frames to smooth them. So instead of sending 60 frames a second, I only send 12 frames a second, but I'm able to smooth it on the client so that it doesn't look like it. It would be a little bit weird. Yeah, I can't really demonstrate this very well. It does mean that the controls are a little bit behind, a little bit laggy, which is unfortunate, but that's what you have to do in order to get smooth stuff. And just for fun, let me try changing the frame rate. So that's what it looks like actually at 60 frames a second. And it probably looks just about the same as if we were interpolating. But note, the bandwidth has gone up substantially because we're sending so much more data. Okay, back to the fun part. Bandwidth is the easiest to address. You decrease the frequency of packets from the server. You use interpolation to smooth things out. But it can be problematic if latency is fluctuating because that latency affects when the packets come and go. We can also address flaky latency by keeping track of every frame and storing it for a few frames on the client before applying it to the game. And we can even run the player's actions locally so that their own actions don't feel like they have any lag. And even run the server-side simulation on each client so that all of the clients feel like they're actually running it in real time. And if any authoritative data comes from the server that conflicts with the client's data, the client does weird stuff to fix it. So this is how most first-person shooters over the internet work. And then on the other side of the spectrum, we have something where every client has to stop and wait until it gets updates from all of its peers. So every frame executes on every client at the same time in lockstep. This is effective for large, complicated games like real-time strategy games, but it does mean that if any player gets out of sync, then all the other players suffer, and you have to get floating point determinism working, which is one of the unsolved problems of physics. So this right here is a website that explains all of the different networking models that you can use for your multiplayer game. And you should go check it out because it's very interesting, lots of fun things that I discovered from that. This guy wrote the book on networking, real-time networking, so check it out. Okay, that is everything. If you want my slides and that Pong demo, there's the QR code. Thank you for coming.